I'm Paul Fadler and this is Lucia Herra from the German team, and we want to present our findings on problem number 3, ink tree. As is stated in the task, when a small drop of ink is dropped inside an especially still beverage of water, it sinks, forms torus-shaped rings, which after some time and sinking down collapse. And the collapsing tori form new droplets, which again form new tori, and the whole thing repeats and the structure becomes self-similar. The task states that the maximal number of ring divisions is to be investigated and its dependence on the important parameters. Okay, at first we're going to have a theoretical look on why these tori collapse. They in the first place form because on the boundaries of the drop there's friction, which causes an inward flow of the ink that has to come down somewhere. That's why two circulations at the edges of the droplet form. And as the droplet flattens because of the higher friction at the higher slowdown at the bottom of the droplet, after some time the drop structure breaks, a hole opens in the middle, and we get a small torus. The internal fluctuations in the torus become bigger and bigger over time, and the structure will become unstable, which causes them to collapse and form new drops, which go through the same evolution. Okay. There are two important things working on the droplet. One is the convection and one is the diffusion. The diffusion will be neglected in our investigation because we found these structures and droplets inside the beverage to be relatively stable. They dissolved only after a time much longer than the actual phenomenon we observed. On the other hand, we have a Magnus effect-like force on the torus, which causes it to widen as it sinks. It can be calculated using the Kutter-Zukowski theorem, and we get a differential force for a small differential angle of the torus. Putting in that the volume of one of these tori is conserved, we end up at this differential equation for the radius of the tori. As you can see, for any initial radius, this is going to go towards infinity. What does that mean for the torus? It means that the torus will become smaller and smaller, and because on the boundary the sinking speed of the torus has still to be equivalent to the rotational speed, the speed profile inside the torus is going to become more and more steep, up to some point where the structure becomes unstable and will inevitably collapse. What can we conclude from that? There has to be every torus will collapse. So for the structure to stop, there has to be some point where the droplets can no longer form tori. Therefore, such a minimal volume has to exist. Unfortunately, we were not able to calculate this minimal volume through our theory, but through our experimental investigation, we were able to determine its approximate size.
Yeah, so I'd like to continue with some of our, first with some of our quantitative observation. So what happens if we put a drop of ink into a glass jar? So at first, as you can see up here, it forms a torus, and when that happens, we observe that the sinking speed decreases, and then some small dents appear in the torus, and those dents then form new droplets, which then transform into new tori. And all in all, this forms a tree-like cascade structure. And in the end, it can happen as you can see up there, that the connection to the primary torus of the subtori dissolves. But this is only the case if the subtori are small. For bigger tori, actually the opposite thing actually happens. It happens that ink flows down into them. And you can see a nasty example actually of this here, because this can lead to ink flowing down in just one of the tori, and then this can tilt the whole structure. This is one of the possible disturbances we observed. Other disturbances are uneasy water, which can cause the structure to just to drift around or to rotate. And also it can happen that when we insert a drop of ink that there's a secondary structure which remains at the surface. And we observed that all those effects actually hinder the formation of branching. Let's continue on some of our important parameters. The most important parameter we considered is the drop volume, and there we clearly observed that the bigger the drop, the faster it spins and branches, and the more subtori and cascades form, as you can see here in the comparison between 0.5 and 2.5 milliliters. You can clearly see that there's more structure down here. Thereby we come to our hypothesis, which is also supported by theory, so that there exists a minimal droplet volume below which no droplets can form. And an open question we will address is, on what does this minimal droplet volume depend? So let's consider another parameter, temperature. We observed that at higher temperatures the ink structure dissolves faster. And our hypothesis is that this is due to diffusion in the water, because we have higher diffusion with higher temperature. So I'd like to introduce our setup. So we used a cylindrical container with distilled water, that with 8 centimeters in diameter, and to control the droplet size we used a microliter pipette. And we placed the drop just below the surface, then filmed the whole process, and in the end we stirred the water and waited until it was calm again, and we changed the water so often that the ink concentration in the water stays below 0.01%. So we can always assume that the water is clear. So then briefly talk about our method. So we estimated the number of tori in each cascade step relative to the step before. So for example, you can see here in the first step there are 8 tori. Then some of those tori branch again. If we count again in the second step, we count 12 tori. So there per tori in the first step we have on average 1.5 tori in the second step. And here we observe no branching in the third step, so our factor would just be 1. And then for the minimal droplet volume, we assumed that the ink is distributed evenly at each partition, and then a drop can only split if it has at least twice the minimal droplet volume. So on average, a drop that doesn't split will have 1.5 times the minimal droplet volume, so we can calculate it from a droplet that doesn't branch the minimum droplet volume. So let's come finally to our results. Here you can see how the initial droplet volume is related to the mean number of cascade steps, and as you can clearly see, the number of cascades steps, how far it gets down, increases with the droplet volume. Then let's look at this plot. Here we observe the mean number of tori in each cascade step, and you can see that it decreases very fast. So in the first step we have, for example, 8 tori, and then, as I have shown in the example before, in the second there's only 1.5. So it's a really rapid decrease. But is this exponential? Exponentially, because it looks exponentially, but actually it isn't. For an exponential factor, it would be required that this factor, so the number of steps, the number of tori in the next step, divided by the number of tori in the step S, is always the same. But this is not the case. It clearly increases, and this points toward a mechanism that makes the production of tori less and less efficient with each cascade step going down. And in our opinion, this strongly indicates that we have a minimal droplet volume here. So let's come to the minimal droplet volume. I described before our method, how we estimated the minimal droplet volume, and here you can see our results. So you can see that the minimal droplet volume is not constant, but decreases clearly with the size of the initial droplet. And our main hypothesis is that this is due to the higher sinking velocity of the initial droplet. So to sum up, The maximum ring division we observed was 4. We observed also that the minimum droplet volume exists, and then it's dependent on the volume of the initial droplet. Yes. Here are my reference, and I'd like to thank you for your attention.
Thank you.
Well, first of all, thank you for this presentation. We'll start with some of the good points of your presentation. You gave a very good explanation of the theory behind the phenomenon, a pictorial presentation, as well as the forces acting on the drop of ink and the torus during the experiment. You also explained very good how the torus forms and how the Magnus effect plays a role in this phenomenon. And he also studied very well the disturbance in an experimental level of the drop and the torus and how that affects the results. However, you neglected the diffusion completely, which actually plays a role in bigger depths, and you can actually find some times, characteristic times, and so on and so forth. We'll discuss this later. You ignored the instabilities, like Rayleigh-Taylor instability, which plays a role in how the torus becomes further drops, and the torus breaks up and becomes further drops, and they break up, and so on. There was no explanation of how the torus moves through the water and then breaks up. And by that I mean with equations, with a mathematical background. You did not explain why we see 3 modes or 4 modes or 2 modes. There's no explanation about that. That also correlates to the instabilities. And you did not study certain parameters like surface tension, how that plays a role, temperature, and that goes with diffusion as well, the initial velocity of the ink that you drop it. You did not experiment with dropping the ink from above the surface of the water and how that affects the phenomenon, and so on. And I would really like to discuss these parameters. These are some of the things I want to discuss with you. Like if you change liquid, if you don't put in water, but you put in a more viscous or a less viscous fluid, what do we expect from that? How does surface tension, temperature, the radius of the torus with depth correlate to what we're trying to find out here, which is the levels, like will it make more levels or less levels? How do you explain the number of modes? Why do you get 3 drops or 2 drops? The number of levels, how do the instabilities play a role in this, and how does diffusion play a role in this? I'd like to see some correlation between your experiment, which was very good, with the theory behind it. Like we predict this and we get this. I didn't see any of that, and I think you could do more on that too. And as I said, what would happen if you drop the ink from above the surface of the water, or the liquid in general? So can we move into the discussion?
Sure.
So I'd actually like to start with the last one. It's okay. We tried that. We tried to drop the ink droplet above the surface of the water, but the problem with that was that there always remained ink on the surface of the water, and this is a big disturbance for us because we vary the droplet volume. And if you want to vary the droplet volume, then and it's very hard to estimate the amount of ink that stays at the surface. So we decided to always put the drop of ink below the surface to avoid that problem.
Oh, all right, I understand. But when you dropped the ink from above the surface, did you see more diffusion, less diffusion? Did you see more modes, more levels?
We didn't really research that because the disturbances on the droplet size were too high, and there are rarely any structures formed at all.
Okay.
So in most cases it was just, well, some rings formed, but they were very tilted, and with that kind of data you just can't work. And then we decided that we always put drop in the same point below the surface to have controlled conditions here.
Okay, I understand. Now, you did not study any parameters like let's say temperature, for example. If you increase the temperature
yes,
of the liquid,
well,
what happens?
we studied temperature qualitatively, and then we observed that higher temperatures lead to higher diffusion. So, and as the task states that we want to maximize the number of rings and the number of cascade steps, we decided to just stay at a low temperature.
Which was?
20 degrees room temperature. And that one we chose for practical reasons, because then we don't have any problems with, for example, cooling or heating, because that could, well, lead to additional problems, that there's heat transfer from the water to the air and, well, kind of other kinds of disturbances
but,
we would have needed to consider.
I understand, but you could improve your experimental setup to accommodate for these disturbances, could you?
I think we could. We could try to maybe do it outside or in a cooler room. Well, yes, I think we could improve it that way.
Okay. And you didn't...
We just focused on the droplet size.
Yeah, you didn't discuss at all the Reynolds number, which plays a significant role, because if it relies on the viscosity of the water, on the velocity of the drop leading to the water. So if you have a low number, you have a laminar flow, you can see the modes and the levels. If you have a high Reynolds number, you have a lot of disturbance, you can't see anything, a lot of diffusion, a lot of turbulence. You can't see anything, you didn't...
May I comment on the whole theory aspect that you brought up?
Yes, of course.
The instabilities and Reynolds numbers and all that stuff is very difficult to complicate. And agree on that point.
Yes, of course.
And even to simulate it, you would probably need some calculation time on pretty big computer grids. That's why we decided to kind of put a black box around the whole collapse thing, which you could see, and focused on the aspect that our theory showed that every torus will collapse. It doesn't matter to us how it does collapse.
All right, but the thing is...
The fact that it will inevitably collapse is enough to get the prediction.
Yes, I understand it, but if you study how it collapses, like if you study the instabilities, then you can easily find out how many modes it makes. And I mean, not even if you couldn't do it...
calculate the trajectories of air molecules, you can calculate...
Yeah, no, even if you don't do it computationally, and you do it just theoretically, you didn't say any of that. Like, for example, if you have a liquid with a higher density above a liquid with a lower density, what happens then? You have instability and the two of them mix. Like if you have oil and water, what happens then? You have instability.
When you have oil and water,
if you have water on top and oil on the bottom,
okay.
So the two mix, the water goes down, the oil goes up, and you didn't discuss any of that. How does that happen?
Because it's not important for this 1 minute.
But it is important, because that's how you find the number of modes. And if you find the number of modes, you can see, is it too large so it can break up? Is it too dense so it can or cannot break up? What happens there? So you can see how many levels it will do after that.
The oil-water comparison lacks one major aspect that this experiment does not have. Oil and water are not mixable, meaning there's a surface tension between them. The whole mechanism does no longer work if you have surface tension. Tori with surface tension will not collapse because the surface tension will provide an inward force that makes them stable at some point.
The oil and water analogy was so I can present to you how the instability works. The thing is that you have still a liquid of high density, which is ink, and liquid of lower density, which is water, and how these two mix, which they do mix.
I'll report. Yes. Good evening, everyone. Good afternoon. My name is Oskar Karlsson, and I will be the reviewer for this interesting discussion and presentation. We have already seen the problem description, so I will not go into further detail about that. So, for the summary of the report itself. The report is focused on finding the maximum number of rings, which is the problem stated, as dependent on the important parameters. They present a theory for ring formation about the friction between the ink and the water, and says that the drops become unstable, although they don't give any theoretical motivation as to why this breakup process happens. They claim to negate diffusion and then comment on this later on in the presentation. They also present the Kata-Zhikovsky theorem for the Magnus effect, and claims there's a minimal drop size for this split-up process, but did not calculate, but rather observe from the experiments. For the experiments, they make qualitatively observations for ring branches, and they correctly finds that any disturbances of this process prevents further branching. Observe that bigger drops fall faster, and that higher temperature gives higher diffusion. They present a experimental setup, but didn't really account for how they collected the data. They varied some parameters, among others drop size and temperature, and observed that the number of cascade steps increased with the volume of the ink drop. And also makes the claim that minimal drop size decreases with the initial drop volume. Points raised by the opponents, they made good praise for the theoretical model, although commented on there was no physical explanation for the movement nor the breakup process in and of itself. Further commented that the diffusion was neglected, brings up some fundamental physical effects dependent on diffusion, really tailoring stability, and brings up the parameters that were not varied. Also notes a lack of connection between theory and experiment. So, evaluation of discussion, drop height was discussed, temperature choice, Reynolds number, not comment on the collapse process, and focus on what was not done. So, for the points to discuss, I want to discuss the physical process of breakup, and I want you to discuss the temperature dependence, since you claim it was the most important parameter. Also, I want to discuss the density difference between the ink and the water itself. So, let's start with the process of breakup. Do you have any ideas for the physical process? Let's start with the reporter and then the opponent.
Okay. These torus structures in itself are pretty stable. You probably know those experiments with the ton and the air vortex. They remain stable for a pretty long time. So, in order for these structures to break up, something has to happen. And we calculated and observed the fact that these structures widen over their time evolution. And as they widen, the velocity gradient inside the torus becomes more and more steep, resulting in the structure becoming no longer stable enough for small enough disturbances. Like one point of the torus might have a little more ink, sinks faster, and therefore...
Yeah, we also observed that in the experiment, as I said, right in the beginning of the qualitative observations, that we observed that the smaller dents and the smaller droplets tend to lose the connection to the primary torus, and the bigger ones tend to get bigger, and because ink flows down into them.
Yeah.
The opponent?
Yeah, I have a question. Is this the process that the drop of ink develops into a torus, or a torus develops into more?
The torus breakup.
The torus breakup.
Yeah.
Well, in the torus breakup, what happens is that at some point you have increased vorticity. So you have the torus is non-homogeneous. So at some points on the torus you have more density, more ink particles, if you will, and on some others you don't. And so this creates some points on which these particles fall. And this is how the torus breaks up, and this is described very accurately by the instabilities I mentioned earlier.
Okay.
May I
Yeah,
add
sure.
one more point?
Sure.
If you look at the experiments, you can also see that the points of breakup where the new droplets form are almost always periodically around the torus.
Okay.
We tried to model this in a theory as standing harmonic waves on the torus and with a linear stability analysis.
I must ask though,
okay.
Is it possible to create a stable vortex ring with a density difference in a liquid?
Not with two mixable fluids.
Okay. You?
Yeah, I agree, because when the torus forms, it has a velocity, and what actually happens, if I will for just a moment, you have a velocity that goes down, which is the vertical one, and you have an angular velocity, so it expands, and so you have this difference.
Sure. for the temperature difference, you claim this was the most important. Explain why, and then you can get your...
It is the most important for this experiment with water and with ink, because if you change the liquid, other parameters come into play, like viscosity and so on and so forth. Temperature is very important because if you increase the temperature...
I must ask, ink or water, or the ambient water temperature?
The water temperature.
Okay.
The water temperature. If you increase the water temperature, then you have great diffusivity, and then the phenomenon breaks up. Well, the levels become less, and at some point you don't see the phenomenon.
We are short on time.
Yeah, that's what I also observed in the qualitative observations. And as I said, I wanted to maximize the number of drops and levels. And this is why I concentrated on one temperature.
Yes.
I really could control very well.
And a
so
short
I think
comment,
we discussed it.
very short comment on temperature difference. You go first, and then the opponent. Is the difference of the ink and the water? How the short answer does that affect?
I think yes, because of the viscosity change.
Okay.
Yeah, exactly, because
yes,
there's a big temperature difference.
Do you think the reporter solved the problem?
If they solved the problem, they did not answer theoretically and correlation with experiment what they saw. They answered how many levels they saw,
okay.
But that's it.
General discussion, if anyone wants to join in, that's completely fine and actually very appreciated. So if not, then you can continue with your comments on the...
Maybe we can comment shortly on the density difference.
Yes, sure.
If you look at the datasheet of the ink we used, it has a density of 1.01 gram per cubic centimeter, meaning it's all but 1% the same of water. Meaning the structures we observe of the ink are the same as we would observe if we put a water droplet in the water. We only don't see that droplet.
Yes, but the difference is that the velocity of it does make a difference, and actually there's a slight difference of 1%, as you said, but that's what makes all the difference, isn't it? Because when you drop it in the water and it has even a higher density, it will create all these effects. If it has the same density, it will not.
I agree on the point that there will be a difference. Maybe I stated that a little.
We have just a comment.
The reporter. Do you think that some stability techniques like Rayleigh Taylor or something like that could be useful to study the breakups of the molds?
Yes, definitely, but it
Just,
will become...
just to be clear, are everyone here familiar with the term Rayleigh-Taylor instability? Yes, good. Continue.
But it will become difficult to solve. That's why we didn't consider the describing the breakup process as it happens, but try to get a description of the whole phenomenon without looking at this point.
Yes. Sure. Since we have no more, do you have any further comments to raise on the density difference?
Okay.
In
the beginning of the drop, the velocity of the ejection velocity will not differ between the ink and the water, but of course you're right. The small difference will result in an acceleration downwards, and during the latter parts of the structure there will be a difference.
Yeah.
I'm sorry.
I glanced at your references, but I didn't quite catch it. Did you read the paper made by J.J. Thomson?
I am not quite sure which you mean. And
from 1886.
I think that was the one with the drawings of the falling tower.
I can say it was not in the references page.
Okay. Because they observed a stable ring-like structure, single torus, for 8 minutes. Do you have any possible explanations?
What parameters did they use?
It was a very small density difference between the ink and the water.
Okay.
They were miscible fluids, the water was still. Yes?
What temperature of the water was used in that case?
The water was left in the room for like...
Temperature?
Standard room temperature for 1886. They didn't comment on the specific temperature. So I would guess somewhere around 18 degrees Celsius.
Can I ask something else on that? What was the initial velocity that they dropped it?
They dropped it from around 4 centimeters.
Did they
if I
drop
remember
a
correctly.
torus or a blot of ink?
A blob of ink.
Did they comment on, was there any comment in the paper on how the structure dissolved after 8 minutes? Did it disperse like through diffusion, or did some tree-like structure appear?
Diffusion, if I remember correctly.
Okay, then our theory would include that case because, no, sorry.
You have a question?
Yes, yes.
To the reporter team, you said that you observed self-similarity in this experiment. Why do you think this experiment produces self-similarity? Why does self-similarity happens in the steps? And when does self-similarity stops to occur?
Well, as I stated, or as we discussed actually, we have the instabilities. As the torus becomes larger, there tend to be more instabilities, and then we get those dents, and then the dent forms a new droplet, and then this droplet, by the same process as the first torus forms a new torus. And this is why we get a self-similar structure. And you asked why it stops. Well, that's actually our hypothesis about the minimal droplet volume. So we say that below a certain volume of the droplet, no new tori can form, and this is why.
Did you try putting a very small droplet near your critical volume to see if it will not break up?
No, that's question.
Well, the problem was that we couldn't actually, because that's I think 10 to the minus 2 microliters, so it's really, really small volume, and we couldn't directly do this experiment.
All right. Now we have 1 minute for maybe conclusion by the report.
Yeah, so thank you all for this interesting discussions. I think we raised some very good points that we could improve. On the one hand, on the experimental side, so that we maybe could also focus on some other parameters that we did not include in our setup. And I think also there was an interesting discussion about the theory, so whether we can actually model the number of modes, because this is something we did not consider yet. And I'd like to thank you all for this interesting discussion.
Thank you. All right. Let's move on. We have 6 minutes for the jury questions, and we have question number 1.
I have small questions to the reporters. Why does ink sink in the water?
The density is
The
slightly
density
bigger.
of the ink.
Yeah.
Okay. What is the density of ink? Give me please
1.0
just the number.
gram.
Write down.
Yeah,
And compare it with the density of water.
it's 1% difference.
1% difference.
Yes.
Okay. Why didn't you tell it in your presentation? If 1% is so important, why I didn't hear in your presentation?
The important thing is that for the outward force is that there is a falling velocity for the torus. The exact
That's all.
amount of the mass excess of the ink only would increase. As long as there is any difference, the torus will split. It's only a matter of time, and that's probably why they didn't observe, or why they observed a very longly stable torus in their experiment, because the density was probably even smaller. The fact that there exists a difference is important for the further splits, and how big it is doesn't matter.
Please show 5
Okay.
slide.
Thank you.
Slide 5?
The next question, please.
Which one?
5.
To ask
And
Jason.
meantime, you will show us the time.
I would like to ask Jason if he thinks that it is feasible for an enthusiastic undergraduate to develop a theory that would match the results which were presented in the report.
It depends on what level you develop your theory. For example, if you study how the radii of the modes differ regarding to depth, you could get an expression of perhaps an empirical expression of how you get this and predict this. Moreover, if you see the velocities of the modes as they drop regarding to depth, you could also derive an expression. I think it would be exponential, I'm not sure, on how they slow down as they move downwards into more depth.
Thank you. The question regarding slide number 5.
Question for Ocon. The only formula which contains the densities of these two substances is here.
Yeah.
Yes. And you say that the theory is very
Precise.
precise.
No, no.
Where is the theory?
No, no, no. I didn't say that. Perhaps I was not clear. I meant the theory of how the torus forms. Not
where is the torus formed? Where is the mechanism of torus formed?
in the previous slide, they made a very good representation. Yes.
This is fluctuation of X.
No, of the forces acting on the torus and how this creates an upward movement, and it creates the torus. That's what I meant.
Where is the equation which did explain the forces?
Yes, it was a pictorial representation of the theory, a good pictorial representation of how it acts. That's what I meant.
For the answer. Next question. Yeah,
The
please.
first short is about for the reviewer. What do you think? What did you want to bring by mentioning this article during this last minute of the discussion?
I was wondering if these had any physical explanation. The reporter claimed every torus is unstable, and yet they observed, and yet Thomson observed a stable ring for 8 minutes. And I was wondering if they had any physical comments on that.
Right. And for the reporter, I understand from your presentation that the minimum volume for which a torus can form strongly depends on the sinking velocity of
Yes.
the droplet.
But
Is this correct?
this is our hypothesis, so we couldn't confirm that, but this is our hypothesis.
There's also no
Yeah.
prediction from the theory for that, but that's what we experimentally measured.
Yeah.
And how do you measure the minimum volume of the droplet?
Can you go to this? I explained by the my slide with the where I showed my method. So we assume that the ink is distributed equally among all tori, and so if I
Okay.
if, for example, we have 8 tori, then I assume that each subtorus has the ink volume of 1/8,
Okay.
and then it goes down like this. And then I said that these are actually the tori that don't branch, and a torus also doesn't branch if it has, for example, 1.9 times the minimum. This is why there's 1.5.
So you assume the minimum size as a division of the initial size among the different torus?
Yes.
Let's move to the next question. We have time for
Yes,
it.
small question to the reviewer. How do you think, did reporters solve the problem or not?
I think they, if I may present my own opinion, in my studies I've encountered the difference to be the most critical parameter from the ink to the water. And since that was not considered, I say they missed at least one very important parameter.
Thank you. And
Question
the last
to the
question.
reviewer. You insist that the opponent explain his only theory, his own theory. Is it your rule or not? Coincide this dimension to your role as a reviewer?
Since the opponent claimed that they found that the temperature was the most significant parameter, I found it the most interesting part of I found it an interesting part of the discussion to make the opponent explain this observation.
I understand.
Okay. We're out of time for questions. So we conclude this thing with putting the grades. And thank you.